Hello. Hello. Am I audible? Oh, okay. So I hope you all have watched the lecture videos. So today I'll be discussing the practice assignment sheet that is given on the portal, which is not included in your grading. So that will help you to solve the quizzes that you'll have to submit for the grading course. Okay. Uh, I hope my screen is visible. Hmm. So please keep responding if you have any doubt. Please let me know. If at any point you don't understand what I am saying, I'll repeat it. English, Hindi. Anybody has any problem in Hindi or English? अगर English में समझ नहीं आ रहा है तो I can explain in Hindi as well. Hmm. So let's start. Let's look at the first question. Question number 1. Let let V is equal to C01, the space of all continuous functions defined on closed 0 to 1 with the supremum norm. The sequence, sorry. So the first set of questions, they are asking whether the following are true or false. State whether the following are true or false. First part, let V is equal to C01, the space of all continuous functions defined on closed interval 0 to 1 with usual supremum norm. The sequence Fn, where Fnx is defined as sine to the power nx, is Cauchy. So can anyone guess whether this sequence will be Cauchy or not?
I think it's not a Cauchy sequence.
So how do you get that idea?
Because the limit is discontinuous.
Yes, the pointwise limit is discontinuous. Good. So let's observe this function. We have f fn0 is 0 for every n in n. Fn at, sorry, this function I've written it wrong. This is sine n pi x. So Fn at 1 by 2 would be 1 for every n in n, and Fn at pi, sorry, 1. Fn at 1 is equal to 0 for every n in n. So all the functions will be of the form so our F1 is basically sine x itself. F2 is sine square x, because the values are less than 1. So we can see that. See here, F1x is sine x, sine pi x, and F2x is sine square pi x, which is square of f1x. Now we can see that all the values of the function f1 are between 0 and 1. That means this square will be lesser than value of f1 at x. So we are getting a decreasing function, decreasing sequence of this form and so on. This implies we can say that the pointwise limit fnx will tend to fx, where this fx is equal to 1 at x equals to 1 by 2, and at rest of the points it is 0. This function is not continuous, which gives us an idea, because if the sequence were Cauchy, then in C01, since C01 is Banach space, we know that this Cauchy sequence must have converged, but it must have converged to its pointwise limit. But the pointwise limit is not continuous. It is not in the domain. That gives us the idea that the sequence is not Cauchy. So let's go to its formal proof. For every n in n, let xn belonging to 0 to 1 be such that fn at xn is 1 by 2. So I'm taking the set of, I'll just draw. This is 1 by 2. I'm taking x1 is this point, x2 is this point, and so on. So this tells us that fn plus m at xn, see, if f1 is 1 by 2 at this point, we can see that at rest of the points, at this point, the rest of the values, the rest of the functions are giving value less than 1 by 2. See, if at x naught, f1 x naught is 1 by 2, this tells us that f2 at this point will be strictly less than 1 by 2, and so on. So we have fn plus m strictly less than 1 by 2 for every m positive. So this gives us the supremum norm of fn minus fn plus m, which is greater than equal to supremum m positive mod fn x n minus fn plus m x. This is just by the definition, because we have taken just a subset. Now this is equal to limit m tending to infinity fn xn minus fn plus mx, because fn xn minus this is xn n plus m xn is less than equal to fn xn minus fn plus m plus 1 at xn. That means this sequence in terms of m is an increasing sequence. That means the supremum is attained at the limit. That is why I could replace this supremum by this limit. Now since the first term is independent of m, this is just 1 by 2 minus the second term. We can see that it is pointwise tending to 0. So this is 0, 1 by 2. This tells us that norm fn minus fm, n plus m infinity norm is greater than equal to 1 by 2. Hence, this sequence can never be Cauchy. So is the proof clear? Can you please tell me if
Yes.
okay. So I hope there was no doubt in any of the step. So therefore, the statement is false. Let's move to the next part. It says that V is equal to C01. Again, the set of the space of all continuous functions defined on closed interval 0 to 1 with some different norm, where norm 1 is defined as integration 0 to 1 mod ft dt. Then Fn is Cauchy, where Fn x is equal to x to the power n. So can you please check whether this sequence is Cauchy or not in this norm? I can wait for 2-3 minutes. Just let me know whether it is Cauchy or not. So is it coming out to be Cauchy?
Yes.
Okay. So how did you proceed? Can you give some idea? Basically,
I
yeah,
think we can take the F1 norm. I can can show that for any epsilon greater than 0, there exists an n such that norm of Fn minus Fm is less than epsilon.
yes. So all we need to show is the basic definition.
Yeah.
Let n and m belonging to n. We have Fn minus Fm norm 1. This is 0 to 1 mod Fnt. This is Fn minus Fmt dt, which is 0 to 1 mod Fnt minus Fmt dt. Now what is Fn? This is just t to the power n minus t to the power m dt. Now suppose without loss of generality, I take n to be greater than n. Now since n is greater than m and t is between 0 and 1, this tells us that t to the power n is less than t to the power m. So this modulus can be written as 0 to 1 t to the power m minus t to the power n dt. Now we can just integrate. After integrating, we'll get 1 upon m plus 1 minus 1 upon n plus 1, which will tend to 0 as n and m tends to infinity. So is it fine? Therefore, the sequence Fn is Cauchy. Hence, our statement was true. Let's move to the next question. So, does anyone have any doubt? This was basic just. Sorry. In the discussion section, does sir himself replies to our doubt? No. For discussion sessions only I'll be solving your doubts. Sir will be taking just the main theoretical lectures. The discussion will be done by me. Okay. Let's move to the next question. Yeah, in Google group discussion sections, I think the sir will also be included in that. I don't have idea about it. Let's see the next part. Let n greater than equal to 1. Define phi n x is equal to 1 for x belonging to minus n to n, 0 for x belonging to r minus n plus 1 to n plus 1, n plus 1 minus x, where x belongs to n to n plus 1, and it is n plus 1 plus x for x belonging to minus n plus 1 to minus n. Let f belongs to BUCR. This is the space of all bounded and uniformly continuous functions on R. They are saying the sequence phi n f is convergent with respect to the supremum norm. So can you guys try it once? So suppose Gn is phi n f. First, let's start with plotting this function phi n x. So we can see that the function phi n x from minus n to n, this is equal to 1. From n plus 1 to infinity and minus n plus 1 to minus infinity, this is 0. And in between, it is the straight line joining these 2 points. For every n in n, phi n is something like this. So can you tell whether this phi n will converge pointwise? What will be its pointwise limit? Can anyone tell me the pointwise limit of the functions phi n? See, these functions, we plot them together. Let's see. This is -1, 1. The function f1 is something like this, -2, 2, 0. This is our f1, sorry, phi 1. Phi 1. What is our phi 2? Phi 2 is equal to 1 from -2 to 2. -3, 3. 0, 0. Similarly, what will be phi 4? It will be 1 in a more bigger set and then 0. So we can see that its pointwise limit is 1. Good. Therefore, phi nx tends to 1 for every x in R. So can you tell me whether it will be its uniform limit as well? Will it converge uniformly? This is our pointwise limit. What about uniform convergence? Will these functions, the sequence phi n, converge uniformly as well? So because if it is uniformly convergent, then it must converge to 1. And in that case, we will have Gn minus f infinity norm is equal to phi n f minus f infinity norm, which is f supremum phi n minus 1. So suppose if the function is uniformly convergent, if the sequence phi n is uniformly convergent to the function 1, in that case this will tend to 0. And since f is a bounded function, this is a constant, so eventually this will converge to 0 and we have Gn converging to f. So all you need to check is whether this sequence of functions phi n converges uniformly or not. So can you try? So one of the student is saying yes by Weierstrass criteria. Can you please explain me?
One question I have.
Yes.
Could you explain how did you write sup norm of phi n of f minus f will be equal to
This
sup
will be
norm of f?
less than equal to, sorry.
Yeah. But can we write this? Can you explain this part? Why can we write this?
Go by the definition. This is supremum of mod phi n fx minus fx for all x in R. So see this, all such terms, phi n x fx minus fx. We can take this fx outside, modulus fx, phi n x minus 1. Now this fx is bounded by its supremum norm, phi n x minus 1. This is irrespective of x for all x in R. So therefore the
Just
supremum
a
will
minute.
also.
Isn't it phi is working on f of x? It's like a composition function.
No, I think it's multiplication.
Oh, is it?
Phi n f, it's multiplication.
It's multiplication. Okay, okay. Thank you.
It might be composition as well. I Okay, we'll do one thing. I am also getting confused. Maybe it's composition as well. Let's take this as multiplication only and do that way. So is this sequence of phi n uniformly convergent? What is it? Sorry, it works. There is not some fn here. I'm sorry, I'm not getting what you're saying. Now suppose this function, this sequence, let the sequence phi n converges to 1 uniformly. Well, in that case, for epsilon equals to 1 by 2, there exists some n naught in n such that mod phi n x minus 1 is less than 1 by 2 for all n greater than equal to n naught and for every x in R. Because in the case of uniform convergence, this n naught is independent of x. Suppose it was uniformly convergent, then we should have such n. Now if we take x to be equal to n naught plus 1 and n equals to n naught, then we must have, according to the definition, we must have phi n naught at n naught plus 1 minus 1 less than 1 by 2. But see, what is phi n naught at n naught plus 1? The value of phi n at n plus 1 is n plus 1 minus x. So our x is n naught plus 1. So at point n naught, this is n naught plus 1 minus n naught plus 1 minus 1, which is 1 and greater than 1 by 2. So this gives us contradiction. Therefore, this sequence phi n is not converging uniformly. Is it clear?
One question, could you please repeat why did we need uniform convergence? Can you please summarize the argumentation from starting, please? Sorry.
Yeah, that's what I'm saying. Are you clear with the fact that this sequence phi n is not converging uniformly to 1? Is
Yes,
this
that is
part
clear.
clear?
Yeah.
Okay. Next is your task to see whether this uniform convergence affects the convergence or not. This will be helpful to you. Use the fact that this is not converging uniformly and then check whether this sequence is converging or not. Okay. So I want you to try this. In next class, we'll discuss it. Okay.
Okay.
See how this is affecting the solution. So I'll keep this question on hold. We'll move to the next question. This question is a homework for you all. Is it fine? Let's move to the next part. The closure of C00 in L1 is L. Now what is C00? C00 is the subspace of all sequences such that all but finite number of terms are 0. So what do you mean by all but finite number of terms are 0? Yes? Can anybody tell me what do we mean by all but finite number of terms are 0? What happens in the limit point neighborhood? So that means only the finitely many terms are non-zero. That is, the sequences where only finite number of terms are non-zero. And we all know what is this L1. L1 is the space of sequences xn such that the sum mod xn and from 1 to infinity is finite. So we need to see whether the closure of C00 is L1 or not. So what do you mean by closure of C0 not C00 in L1 is L1? That means if it is equal to L1, in that case, for every x in L1, we can find a sequence xn in C00 such that this xn converges to C00 in L1 if the closure is equal to this. Now, can you tell me whether the closure of C00 in L1 will be L1?
I think so, yeah.
Okay. Indresh, can you please mute yourself? Yeah, thank you. So, yes, this will turn out to be its closure. We'll see how. Now, suppose X is an element in L1. That means it is a sequence K from 1 to infinity. This is in L1. I can construct a sequence in C00. So, let's define it as follows. Xn is the sequence xnk, where xnk is equal to xk whenever k is less than equal to n and 0 for k greater than n. That means if our x was x1, x2, x3, so on, then I have a sequence of sequences where first term is a sequence having first term similar to that of x and rest of the terms are 0. Then I take x2 to be equal to x1, x2 and rest of the terms 0, and in similar manner I construct a sequence. So clearly all these xn's will belong to C00 because we have just finite number of non-zero terms, rest of the terms are 0. Now we need to see whether this sequence converges to x in L1 or not. That means we need to check whether xn minus x tends to 0 as n tends to infinity. This is my claim. And we have norm L1 norm. So let's see what is the L1 norm of xn minus x. This is summation k from 1 to infinity mod xnk minus xk. So can anyone tell me next step? We know that all these x and k's are 0 after n. So this is summation k from 1 to n x k minus xk plus summation k from n to infinity 0 minus xk. Is it clear? Which is just summation k from n to infinity mod xk. Now I am saying that this will tend to 0 as n tends to infinity. Can anyone tell me why? Why will this sum goes to 0 as n tends to infinity? Because we know that x, which is equal to the sequence xk, is in L1. That tells us summation k from 1 to infinity mod xk is finite. And we know that the tail of a convergent series converges to 0. Therefore, the tail of a convergent series will converge to 0. Thus, now since x belonging to L1 was arbitrary, since x belonging to L1 is arbitrary, this implies C00 closure is equal to N. Is it clear? So let's move to the next part. Therefore, this statement was true. Yes, this is
Okay.
true. Yes.
Sorry, ma'am.
Yes.
N equal to xk. Is equal to 1 to n. Equal to xk.
Your voice is disturbing. Can you please write in the chat box? Your voice is not clear. So basically, for any x in L1, we have constructed a sequence in C00 such that this sequence is converging. How is XMK? I have taken this as XK. So we have a sequence X, it has terms X1, X2, X3 and so on. So I am saying that in this sequence XNK, the first n terms are same as that of the given sequence. Okay, and rest of the terms are 0. So is it clear? I have taken the sequence xn in such a way that the first n terms are same as that of the original sequence and rest of the terms are 0. That is why I am taking xnk to be equal to xk. Okay.
Yes, thank you.
Let's move to next part. It is saying that L1 is a subset of LP for every 1 less than equal to p less than equal to infinity. That means if a sequence belongs to the space L1, then it should belong to LP for all p. Can you people just try it? Whether it is true or false? Suppose if it is true, then what do we have? For every x in L1, we should have x belongs to LP as well. For all 1 less than equal to p less than equal to infinity. Take case 1 to be p equals to infinity. In that case, see whether if x is in L1, then it should be in L infinity or not. We have x, a sequence xn in L1. See whether this will belong to L infinity or not. So for a function to be L infinity, what do we need? Sorry, not function, sequence. A sequence is in L infinity. X belongs to L infinity if and only if supremum n in n xn is finite. Now since we have taken x in L1, this implies summation mod xn n from 1 to infinity is finite. So this gives us the sequence xn converges to can anyone tell me? If the series is convergent, then the sequence converges to
0.
yes, 0. Hence, the sequence is bounded. Xn is bounded. This tells us that there exists some m positive such that mod xn is less than equal to m for every n in n. This gives us that the sequence xn belongs to L infinity. Let's see next case when P is finite. We have summation n from 1 to infinity mod xn less than infinity. Check whether summation n from 1 to infinity mod xn to the power p is finite or not. I can give you a hint. Use the similar fact that since the series is convergent, hence the sequence will converge to 0. Use the fact that the sequence is converging to 0 to see whether this sum is convergent or not. So here you can see that this gives us the sequence xn converges to 0. That means after a stage, you can, for every epsilon positive, you can find a stage such that after that, all these elements in the sequence are in epsilon neighborhood of 0. That means we can find some n naught in n such that mod xn minus 0 is less than 1 for every n greater than equal to n naught. That means mod xn is less than 1. Now what can we say about mod xn to the power p and xn, where p is greater than equal to 1. So what inequality will we have here? Can anyone tell me? When we have numbers lesser than 1, in that case xn to the power p, let's start with x square. So if our number is less than equal to, for p, for x, if a is less than 1, we know that a square will be lesser than a. In fact, a to the power p will be less than a for every p greater than 1. Because exponential function is decreasing for the whenever this a. You know that a to the power x is decreasing function when a is less than 1. So this is less than mod xn to the power. So this tells us summation n from 1 to infinity mod xn to the power p is equal to summation n from 1 to n naught mod xn to the power p plus summation n from n naught to infinity mod xn to the power p. This is strictly less than summation n from 1 to n naught mod xn to the power p plus summation and from n naught to infinity mod xn. Now this is a finite sum. This is a convergent series. Therefore, this is finite. This tells us that the sequence xn belongs to LP for every 1 less than equal to p less than infinity. Hence, hence L1 is contained in LP. Therefore, L1 is contained in P for every 1 less than equal to p less than equal to infinity. Is this clear? If anyone have any doubt in any of the steps, any of the cases, please let me know. So shall we move to the next question? So till now we were doing some true false questions. Next we have normal questions. So shall I move? Please respond. Let's move to the second part. Answer the following. We have question number 6. Okay. Let n greater than equal to 2 be an integer. Let m and r denote the space of all n cross n matrices with real entries for A belonging to the space M N R. We define this equals to summation ij1 to n aij square to the power 1 by 2, where A is aij n cross n. So our first part says that show that this defines a norm on MNR, and the second part says that show that norm AB is less than equal to norm A plus norm B for every AB in MN. So can you please try the first part? All you need to check is the 4 properties of the norm. First one, positive. Second, norm is equal to 0 if and only if A is equal to 0. Third, norm of alpha times A is equal to mod alpha times norm A, and the triangles inequality. So just for the record, I'll prove the properties. First part is equal to summation ij1 to n aij square to the power 1 by 2. Since we are taking sum of positive terms and then their square root, this should be positive. Second is, if this is equal to 0, this is equal to 0 if and only if summation ij1 to n aij square power 1 by 2 is equal to 0. If and only if summation ij1 to n aij square is equal to 0. Now sum of positive terms is 0 only if all the terms are 0. This tells us aij is equal to 0 for every ij. That means a is 0. Third part, let alpha belonging to R be arbitrary. Alpha times A. So alpha times A means we are multiplying each of the terms of the matrix by A. Alpha, sorry. Ij 1 to n alpha aij square to the power 1 by 2. So we can take this mod alpha outside. We will be left with summation ij1 to n aij square to the power 1 by 2, which is mod alpha times. Last one is the triangles inequality. For this, we'll be using Helder inequality. So let's recall Helder's inequality. I hope you all must have watched the lecture videos and seen how we prove Helder's inequality. This is summation I from 1 to k ai bi is less than equal to summation I from 1 to k mod ai to the power p whole to the power 1 by p summation I from 1 to k mod bi to the power p star to the power 1 by p star, where 1 by p plus 1 by p star is equal to 1. We'll be using this inequality to prove the triangles inequality. So, fourth part, let A and B belonging to MNR be arbitrary. Norm A plus B is equal to, let's take it square, summation ij from 1 to n aij plus bij square. Now this can be written as summation 1 to n aij plus bij aij plus bij. Now we'll be using the triangles inequality of modulus in this part. So this gives us, this is less than equal to summation ij 1 to n mod aij times mod aij plus bij plus summation ij from 1 to n mod bij times modulus of aij plus bij. Because we know that modulus x plus y is less than equal to mod x plus mod y. Now let's apply the Helder's inequality. So this is less than equal to, I will be taking p equals to p star equals to 2. Summation I j from 1 to n mod aij square to the power 1 by 2 summation ij1 to n aij plus bij square to the power 1 by 2 plus summation ij1 to n bij square to the power 1 by 2 and summation ij from 1 to n aij plus bij square to the power 1 by 2. So this is basically norm A plus B. So ideally, I should not be saying it norm because till now we don't know whether this is a norm or not. A plus B E, taking it to be common, we get. And this term is norm A. So this is norm A E plus norm B. So see, on the left hand side, we had A plus B square. So taking this term on the left hand side, we get norm A plus B is less than or equal to norm A plus norm B. Therefore, this satisfies the triangle's inequality. Hence, this is a norm. So, is it fine with everyone? How we proved that this will form a norm? If you have any doubt in any of the steps, okay, good. We can move to the next part. Next part is a bit tricky. Part B. We need to show that E norm of AB is less than or equal to norm A times norm B. So can anyone tell me the ijth term of the matrix AB when we are doing usual matrix multiplication? How can I write the ijth term of the matrix AB in terms of some summation? So this is basically summation k from 1 to n aik bkg. So from here we get abij square is equal to summation k from 1 to n aik bkj square. So this is square of n terms. I mean, this is something of the form a1 plus a2 plus a3 and so on up to an whole square. So this can be written less than equal to square of each term. b1j square plus ai2 b2j square and so on up to ain bnj square plus the multiplication of distinct terms. So this will be plus summation of terms of the form AIS BSJ times AIK BKJ, where this S is not equal to K and all S and K are from 1 to N. S and K are 1 to N. S is not equal to K. Is this clear? I'm just taking square of square after taking sum of n terms. Okay. So let's number this as equation first. Now this tells us norm AB square is equal to summation ij from 1 to n square of ijth term of AB. Now this is less than equal to summation ij from 1 to n summation k from 1 to n mod aik bk j square plus summation sk from 1 to n, where s is not equal to k, ais bsj aik bk j. This is by first. Now let's split this sum. So this is equal to summation I j k from 1 to n aik bk j square plus summation I j s k from 1 to n, where s is not equal to k, modulus ais bsj times aik bk j. Now let's number this as 2. Now what on right hand side, we need norm A times norm B. So let's see how does our right hand side looks like. Now norm A E square times norm B E square is equal to summation ij from 1 to n aij square times summation st from 1 to n bst square. Now since ij and st are independent, I can club them together. I can write it as ijst from 1 to n aij bst square, which is equal to, I'll just split this sum into the form where these two terms, see here, these two terms are same, these two terms are same. So let's split this sum into the part. In the first part, we'll take all those terms where these two terms are same, and rest of the terms will be the second part. So I'll write it as summation ijs t from 1 to n, where j is equal to s, summation aij bst square plus ijst from 1 to n, where j is not equal to s, aij bst square. So now I'll do some what do you say, some replacement in order to make these terms similar to those in the norm of AB. So I'll take here this. Now since j is equal to s, I'll take j equals to s. I'll replace it by some k, and I'll replace t by j. So this is equal to summation ij k from 1 to n aik bk j square plus summation ijst from 1 to n j not equal to s aij bst square. Now we can see that we had similar term here. So this is greater than equal to this minus this term. So by equation second, this is greater than equal to norm ABE square minus summation IJST from 1 to n, where S is not equal to T, AISBT. So there we have BSJ times AIT BEJ plus this rest of the term, summation IJST from 1 to n AIJ BST square. So this is by equation 2. Now we see that here. Okay, let's take this sum. So what we needed, we want only this term. We want rest of the term. If rest of the term is positive, then we can write this is greater than equal to ABE norm. That is what we wanted. So let's denote S is equal to summation IJST from 1 to n AIJBST square minus summation IJST from 1 to n, where here also J is not equal to S, J is not equal to S. Here we have S not equal to T. I'll write it as AISBTJ times AITBSJ. Again, I'll do some replacement so that I get this term to be positive. So I'll take here, I'll replace T by J and J by T. I'll just exchange them. So this is equal to summation IJST from 1 to n, where S is not equal to T, AITBSJ square minus summation IJST from 1 to n, S not equal to T, AISBTJ times AITBSJ. Now we can take the summation outside because the condition are same in both the terms. 1 to n, S not equal to T, AITBSJ square minus AISBTJ times, no, sorry. I'll take this IJ from 1 to n outside. ST from 1 to n, S not equal to T, AITBSJ square minus summation ST from 1 to n, S not equal to T, AISBTJ times AITBSJ. Now you can see that this inside term is basically equal to modulus AITBSJ minus modulus AISBTJ whole square with summation. You can check this Try this with different values of n. Start with taking n equals to 2, n equals to 3. You will get this. So this is equal to summation ij1 to n summation st1 to n s not equal to t modulus ait bsj minus ais btj square. Please check it if I have done some mistake. You can try this yourself, taking different values of n, s, and t. This should turn out to be some square term. So this is always positive. Therefore, we mark this as third. Therefore, by equation third, we'll get ABE less than equal to AEB. So is it clear? Please let me know if you have any doubt in any of this step. This part was a bit tricky. You need to take care of all the terms in the summation. Please go through it again and see if you have doubt in any of the step. I've tried to be very clear, taken all the details. Okay, then let's move to next question. 7th. Let V be a non-linear space and W be a closed subspace of V. First part says that show that if xn converges to x in V, then xn plus w converges to x plus w in the quotient space V by w. V. If U is subset of V is an open set, show that the set x plus w, where x belongs to U, is open in V by. So the first part is a bit trivial. You can start with taking xn converging to x. What does that mean? Norm of xn minus x in V it tends to 0. So next, compute the norm of xn plus w minus x plus w in the quotient space V by w. What I'm saying is, let xn converges to x in V. This implies norm xn minus x v tends to 0 as n tends to infinity. Now we need to show that xn plus w converges to x plus w. Now norm xn plus w minus x plus w in v by w. So we know that this is equal to xn minus x plus w. This is how we have defined addition in the quotient space. And what is this norm? Can anyone tell me? What is the norm on the quotient space? Please don't make me feel I'm talking to wall. Hello? Can anyone tell me? Or just tell me you don't remember. I'll repeat it. This is infimum of norm xn minus x plus w, norm in the space V for all w belonging to w. Now this is lesser than equal to norm xn minus x. Why? How can I write this step? Because 0 belongs to w, as w is a subspace. So we can take this w equals to 0 and infimum will be lesser than that. Now this tends to 0 as n tends to infinity, because this is what we are given. Therefore, xn plus w converges to x plus w in v by w. Next part says that U subset of V is open. We need to show that the set X of the form, the set S of the form x plus w, where x belongs to U, is open. So we know the definition of open set. What does it say? We need to show that S is an open set. That means if x naught plus w belongs to S is arbitrary, then we should be able to find an epsilon neighborhood of this point in the set S itself. Then there should exist some R positive such that x naught plus w is contained in BR of x naught plus w, which is contained in the set itself. So this is what we need to show. Now let x plus w, x naught plus w belonging to S be arbitrary. This tells us that this x naught belongs to U. Now since U is open, by definition, there exists some R positive such that x naught is contained in the ball of radius R around x naught, which is contained in U. Okay, let's mark this as first. Now let y plus w belongs to the ball of radius r around the point x0 plus w in v by w. This implies that norm y plus w minus x0 plus w in the quotient space, this is strictly less than r. This implies norm y minus x0 plus w. This is how we have defined addition in the quotient space. Now, by definition, this is infimum of norm y minus x0 plus w v, where w belongs to w. This is strictly less than r. Now, infimum of a set is strictly less than r. That means we can find a point in this set which is less than r. This implies there exists some w and w naught in w such that norm y minus x naught plus w naught is strictly less than r. This tells us that norm y plus w naught minus x naught is strictly less than r. That means y plus w naught belongs to the ball of radius r around x naught. This is how we define the ball, no? So, which is contained in U. This is by first, because we already know that U is an open set. This implies y plus w naught belong to the set y plus w naught plus w belongs to the set of all those cosets such that this x belongs to U, because this is in U. Now, since w naught is in w, we have this is equal to y plus w belongs to x plus w, where w is in U, which is our S. Now see, where was y plus w? Y plus w was in ball of radius r around x naught plus w. That means we have x naught plus w. This gives us br x naught plus w is contained in S. Therefore, x naught plus w belongs to br x naught plus w, which is contained in S. Hence, S. Now, since this x naught plus w belonging to S is arbitrary, we get S is open in V by W. That is what we had to prove. Please go through this proof again. If you have any doubt, please let me know. All you need to take care is the definition of open set. What do we mean by open set? In an open set, every point has at least one neighborhood contained in the set. That is every point is an interior point. So if that's clear, we can move to the last question of this tutorial. Okay. Let V is equal to BUCR, the space of all bounded and uniformly continuous functions defined on R, with the supremum norm. Norm for H in R minus 0, define phi H F at phi h of f is a function which is defined at x is equal to fx plus h minus fx by h. So this is for every x in R and for every f in V. Let W is the subset of V such that all those functions such that phi h f converges in V as h tends to 0. You can see that as h tending limit h tending to 0 phi h v phi h f is basically the derivative. So W contains all those functions whose derivative is in V. So first part says that if f belongs to W, show that f is differentiable and f dash is in V. Second part, show that if f is in V is differentiable if a function in V is differentiable and f dash is also in V, then f belongs to the set W. So all we need to do is study the definition of derivative and how the convergence is happening in supremum norm. All those things we need to take care of. So let's see the first part. What does it say? If f belongs to W, we need to show that f is differentiable and it belongs to V. V means it is uniformly continuous and bounded. So let f belongs to W. This implies phi h f converges in V as h tends to 0. That means there exists some g in V such that phi h f minus g sup norm converges to 0 as h tends to 0. From here, we know that uniform convergence implies pointwise convergence. This implies mod phi h f at x. So let's write it. This implies 0 is equal to limit h tending to 0 phi h f at any point x minus gx for every x in R. Why? Because uniform convergence implies pointwise convergence. This is equal to limit h tending to 0 fx plus h minus fx by h minus gx. This tells us that limit h tending to 0 fx plus h minus fx by h is equal to gx for every x in R. This tells us that f is differentiable and f dash is equal to g, which is belonging to V by the definition of W. So I hope this first part was clear. It was easy. Next, we need to show that if f belonging to V is differentiable and f dash is in V, then f is in W. Let f belonging to V be such that f is differentiable and f dash belongs to V. We need to show that f is in W. That is, this phi HF converges in V as h tends to 0. That means phi HF converges to some G in V in sup norm. Now, since f is differentiable, and f dash is in V, this implies there exists some G in V such that f dash x is equal to gx. Just for the sake of convenience, I am taking this to be gx. That means limit h tending to 0, fx plus h minus fx by h is gx for every x in R. Now recall the mean value theorem by mean value. Let x belonging to R be arbitrary, then by mean value theorem we know that fx plus h minus fx by h is equal to f dash xi for some xi belonging to open interval x to x plus h. Which is equal to g psi. This tells us mod f x plus h minus fx by h minus gx is equal to g psi minus gx. Now I am saying that this will be less than epsilon whenever h is less than delta. Can anyone tell me why? Which property am I using? I'm using some property of G. Use the fact that G is in V. This is because G is uniformly continuous. Now, since G is uniformly continuous, we have for epsilon positive, there exists delta positive such that mod gx minus gy is less than epsilon whenever mod x minus y is less than delta. See here, xi minus x, xi is in x to x plus h. That means mod xi minus x is less than h. Now if I take this h to be less than delta, what do we get? We get mod g xi minus gx is less than epsilon by this definition. So this is less than epsilon whenever h is less than delta. Similarly, I can do this on the other side of the interval. That means x minus h to x. And therefore, we will get mod fx plus h minus fx by h minus gx strictly less than epsilon, provided mod h is less than delta. And this is irrespective of x. This epsilon delta are independent of x because of uniform continuity. These epsilon and delta are independent of x and y. So this tells us supremum x in R fx plus h minus fx by h minus gx is less than epsilon provided mod h is less than delta. That is the infinity norm, the sup norm fx plus h minus fx by h minus the sup norm of phi hf minus g is less than epsilon provided mod h is less than delta. Now this is the definition of limit h tending to 0. That means phi hf tends to g in v as h tends to 0. Thus, this f belongs to W. Is this clear? This was the definition of our set W. W contains all those f such that phi h f converges in V. This G is in V. We have completed first assignment sheet, which was the first practice sheet. So I have left one question. We'll discuss that in the next class. I want you all to think about it. Rest of the things I have given all proofs in well details. I hope that will be helpful for you to solve your questions. Okay. Okay, then we'll meet next Friday, 6 p.m. Please try that question before coming to the next class. We'll start with discussing that question. Okay, then. Thank you.